Okay, good morning, students. Let's get started. I see only a few students, but let them join when they can. So we won't wait. Let's get started. So let me share my screen.
Sir.
Sorry, but the net is not very good. Okay, good. So you can see my screen?
Sir.
Yes, no?
Sir.
Can you see my screen?
Sir.
Yes, sir.
Okay. So some of you have submitted your assignment. I have noted it down, and the assigned problems I had given, I'll solve and send you. And those who have submitted your assignment, definitely you'll see some reflection in the marks that you get finally. So you should make it a habit of submitting assignments, okay? But no need to submit anymore the previous assignments because I'll be giving you the answers by tonight, okay? All right, now here only I think 2 slides are left. I shared these slides with you yesterday. I don't know if my computer is slow. Okay. So we were talking about synthesis of nanomaterials, how to make nanomaterials. Some people use the term fabrication, but I would prefer synthesis, especially for the bottom-up process. And now if you see in the slide, there are different types of nanoparticles that are shown there, different sizes, different shapes, okay, and different material and such, okay. Now, you see those spherical ones, beautiful spherical ones, they are silica, that's silicon dioxide nanoparticles. Okay. Then here, all these prism type ones, they are gold nanoparticles. Okay, the other one on the right, so gold nanoparticles. And here you see two semiconductor particles. Okay, one is zinc oxide, silica is also semiconductor, zinc oxide and zinc sulfide, but silica is more towards an insulator rather than a semiconductor. Zinc oxide and zinc sulfide, they are semiconductor particles. And below you see these particles where a small bottle is also shown as an inset into the figure. Okay, that shows the color of the particles. Okay, these are actually done in the lab by myself, so these are not taken from any book or anything. So you see here as the particle sizes vary for metallic nanoparticles mostly, you see a change in the color. Okay, I already mentioned that before. So you see the figure there from 10 nanometers to 24 nanometers. We are seeing a variation from reddish, purplish, blue, violet, finally grays. Okay, so this is not only dependent on the size also, but also on the shape. That means these triangular or pyramidal type of particles will give a different color as compared to the spherical particles, even if they are of the same or similar size. Okay, so during these synthesis lectures, we will also try to understand how we can control the size or the morphology. If you say morphology, it means what it appears to you when you look at it. That means shape. Okay, so we call that as a morphology. So the shape and the size can be controlled. And now, since our discussion, for the top-down method, anyway, we know we are breaking it up. So you want 20 nanometer, you break to 20 nanometer. You want 5 nanometer, you break to 5 nanometer. Okay, that way the process is easier. But when it comes to the bottom up process, where you are putting in atoms one by one, okay, and then when you get the size you want, you have to stop the process of the particle becoming bigger and bigger. Otherwise, it will keep on becoming bigger and bigger. Okay, so that's why the control of the reaction that is happening is very important. And there are so many parameters during the reaction itself that can control the size and the shape. That means if you vary those parameters, if you check those parameters, then you can control the size and the shape of the particles. Now, those parameters may include concentration of the reactants, whatever chemicals you're putting in, whether it may even biochemicals, but whatever. The chemicals that you're putting in, the concentration plays a role. The pH of the solution we are making the particles. You know about its pH, right? It basically relates to the acidity or the basicity of the solution. So, the pH value is a negative logarithm of the hydrogen ion concentration. You can check out pH if you don't know on the internet. Okay, so that's very basic school level chemistry. So on the pH, on the concentration, on the temperature of growth, okay, on the excitation source. That means if you're using heat, or are you using light, or are you using ultrasonics? So many different excitation sources are there. Okay, because you need to put some amount of extra energy into the system. That means the atoms moving around. If you put some extra energy to force the atoms to come together, okay, come together and then create the nanoparticles. And then finally, when it reaches the size we want, we have to somehow stop the process of growth. So you see the animation here. Is it working, the animation? Somebody? Is the animation working there? Can someone answer me?
Yes, sir.
Okay, so you can say the animation, right? Okay, perfect. So you see here the process. Let me start from it. Now, yeah, do you see here the atoms are there? Then the atoms slightly big, a few of those atoms come together, okay, and then that sets the ball rolling, means that is the start of the formation of the nanoparticles, and that stage we call it as the nucleation stage. That means we are forming some nuclei, and these nuclei will grow bigger and bigger and become nanoparticles. So that is the nucleation stage. So what happens, all of a sudden there will be 1 billion nuclei forming. That means suppose we are making say gold nanoparticles or silver nanoparticles, or maybe zinc oxide nanoparticles. That means, say suppose we're talking about silver nanoparticle. So we have these silver atoms, free atoms in the solution. Then what happens? Maybe 10 of them come together. So it means not only 110, okay, 10, 10, 10, 10, 10, 10 all over. Okay, a very simple example. Suppose we have 100 atoms, which is practically impossible. I'm just giving you a small example with small numbers so that you can understand. So suppose we have 100 atoms of some material, say silver. Then the nucleation process, suppose out of those hundreds, four of them are coming together to form the nuclei. Okay, four of them going together. That means out of the 100, if you divide by 4, you have 25. That means 25 nuclei formed. You understand? There are no more free atoms. All are forming nuclei. Okay? Individual nucleus. Four atoms together, suppose. This is just an example, okay? Don't think this is actually happening, because I'm just giving you some small numbers. When we are talking about in billions. So we are talking about the very simple way of explaining. So out of those 100 atoms, we have 25 nuclei forming now. Then you see all these are in random motion in the solution, okay? Because all these atoms and even the nuclei, they are not static. Okay, they have a random Brownian motion. They're constantly moving inside the solution where you are growing the particles. That means all these 25 nuclei are now constantly moving, like you see here in the animation. Okay, slowly they are becoming bigger. So these 25 nuclei will then start moving around, and then they also meet each other and coalesce. So suppose we have now saying that 5 nuclei came together. Okay, I'm using numbers that will ease the calculation. So out of those 25 nuclei, if they become 5 groups, finally what? They become, out of 25, they become 5 now. 25 divided by 5, right? So these 5 will move around. Again, they will combine. Maybe all these 5 came together and became one nanoparticle. Okay, then that 100 atoms came together into one nanoparticle. You understand? That's how it goes. And this initial process, I said, is the formation of the nuclei. And then all these keep on coming together, becoming bigger and bigger and bigger. That means initially we started with a nuclei of 1 nanometer, maybe this 1 nanometer nuclei became 2 nanometer next. Then these 2 nanometers started coming together, they became 6 nanometers. And then these 6 nanometers started coming together, they became maybe 15 nanometers. 15 nanometers coming together, they become maybe 25 nanometers or 30 nanometers or 50 nanometers. You understand? Unless we stop at the size we want, they will keep on becoming bigger and bigger and bigger. And finally, they will exhaust all the material, and finally, they become into the what you call as a macro scale. And then they will not remain suspended, they will start falling down. So there is another property that at the nanoscale, there is no effect of gravitational force. Okay, but gradually as it becomes bigger and bigger, the gravitational forces come in, and that's why at the macro level, you won't find them suspended, moving around in random motion. They will start settling down at the base of the container, okay, because they become heavy now, and gravitational forces pull them down, right? So this process from the nucleation to the size you want, that means it is slowly becoming bigger and bigger and bigger, is called Ostwald ripening. Okay, let me see. It's called Ostwald ripening. Just a sec. Uh, just a sec. Let's see if I can write it. Let me take a pen. Okay, this is the spelling. Ah, my screen I cannot see properly. Just a minute. Yeah, there's the pen. It is called OSTWALD, Ostwald, okay? Ripening. Difficult to write with the stylus. Huh? Ripening, okay? Ostwald ripening is called the process of growing bigger and bigger. Okay? So, any type of nanoparticles that you do in the solution phase, and it's the best to do when you are making it bottom up in a solution, the solution is called the solvent. Okay? So, you check that out the properties of solvent also, what is called as a solvent. So solvent is basically something where it simply holds. Okay, it is a medium, it does not change. That means if you make some particles in water, water will always remain as water, it is not going to change, but it will assist or it will hold those particles that you are making. Similarly, you can use alcohol, you can use many organic solvents. All right, so we will need a solvent when you are making the particles in the bottom up process. Okay, as we that is starting with the atoms, because it is easier to separate out atoms in a liquid. Okay, the example I gave you, I think I said before that if you dissolve salt in water, salt is sodium chloride. So if you dissolve salt in water, you automatically see that the salt vanishes, right? The white colored salt you put in water, maybe slightly warm water, then you stir it, and after some time you don't see the salt because sodium chloride is not there anymore. Sodium chloride has dissociated. That is the term. It separates out into sodium and chlorine in the water, right? And that's why you don't see it. Okay, but the properties are there, very much there, because that means for every sodium atom there is one chlorine atom in the liquid. Then you start evaporating. Suppose you already have this liquid where you don't see the salt. You start heating up the water and evaporating out into in the form of vapor. Then after some time you gradually see some salt settling down at the bottom, right? Because the concentration has grown more now, because the volume of the solution is becoming less, and that's why it goes to a supersaturated solution condition. That means it cannot keep all the sodium and chlorine in ionic form or as individual identities, and they start coming together again, forming sodium chloride again. And if you keep on doing that, finally if you completely remove the water, you'll get back your original salt. Everything will come back. Okay, so for the bottom up process we will do something very similar. Now in this slide, I've shown you so many different types of nanoparticles: semiconductors, metallic particles, okay, insulating particles like the silica. Now, all these were synthesized. Now, all these are from my lab, okay, when initially when I was working, these are all my cooking. I call it cooking because I put a lot of things together and this is the end result, all right? So, you might say, or you might ask, I don't know if that mind thing has come to your mind, that you are showing in the bottle the color of gold, red, green, yellow, or whatever. You're actually, why is it in grayscale? Why is it not the color that is shown in the bottle? Now that is something you think about. I will explain to you definitely, but I want you to come up with these small questions. Okay, things should come to your mind immediately. Why am I saying it in black and white or grayscale? It won't be black and white, it will be grayscale. So why are you seeing that? Okay, so I'll explain to you when the right time comes to explain this. But these images that you see are taken at a very high magnification. Some maybe 50,000 times, some maybe even 100,000 times, and maybe even 1 million times of amplification or magnification. Okay, and these images that you see here, if you look at it, they appear very two-dimensional, right? Flat type of images, and these are taken using a microscope which is called the transmission electron microscope. I'll explain all these gradually, but this image is taken using a transmission electron microscope. Okay, and any image taken by an electron microscope is always grayscale. Okay, you'll always see it in shades of black and white. Okay, and the TM image or electron microscopy image is a two-dimensional. Then I'll explain why it is two-dimensional. Okay, now if you look at the next slide, here you see the images are more 3D now, right? It's just like a typical digital camera taking a picture, right? Here you can get the 3D feeling. Now these images are taken by an electron microscope which is called the scanning electron microscope. Okay, the difference in technique, the technology is different from the previous one and this one. The previous one was the transmission electron microscope, and this is a scanning electron microscope. But in both the cases, you see the images in grayscale. Okay, now see these images here. You see so many different shapes, right? Particles, then they have rods, different types of rods. Some are tapered rods, then some are big ball-like structures. You see this one uh, here, this one. It is actually a structure which is my creation. Okay, so this is the first report came from me, and looking at the shape, me and my supervisor, we decided to call it the broccoli structure. It looks like a broccoli, right? That's the side view, you see, is a broccoli structure. So the first report of broccoli structure was done by me and my supervisor because this is the creation that came in. And these are like cigar-like structures, okay? Very thin wire-like structures. This is a star-like shape. This is a flat plate, okay? These are flower-like with rod-like petals, and these are flower-like with a different shaped petals. You see all these. This is only, I will say, 50% of the different shapes that I could make myself. Think about so many thousands of scientists working in this area. Only one person could make so many different shapes. Okay, so I made some flat tape-like structures, some triangular structures. Okay, variety. I'm just showing a few of them. And interesting thing, what I'm trying to say here is that all these materials, all these nanomaterials that you're seeing of different shapes, they are all of the same material, zinc oxide. Okay, it's a semiconductor, and all of them are made in a similar process. All right, except the first one, that is the nanoparticles, which is made in an alcohol solvent. There's a reason for that, I'll tell you. But all the others, from the second to the last one, are made in water. Okay, that is one common thing, that all of them are made in water. All of them have the same sources. That means for zinc, I had put in zinc acetate. Some I have put in zinc nitrate also, but it's a salt of zinc. Okay, that means zinc nitrate is a salt of zinc in nitric acid. Zinc acetate is a salt of zinc in acetic acid. Zinc chloride is a salt of zinc in hydrochloric acid. All right. So any type of salt, it's the same. That means I had zinc in water, and I had put in some source of hydroxyl ions, OH. All right, that is sodium hydroxide or potassium hydroxide or ammonium hydroxide. That means sources are zinc from a zinc salt and hydroxide from an alkali. All right. So same starting material, but you see so many different things happening in water itself. How? It's by controlling, like I told you before, the parameters, the concentration, the temperature, the pH, the growth time. Because see, all these, if I show you here, this crystal, because this is a crystalline material. This crystal, if you look here, you see there are different faces. This is a top face. These are side faces. There's a bottom face. So all these different faces of the crystal, they grow at different speeds based on the pH. That means for a particular pH, I'm saying that I'm keeping the pH at 10 maybe. Maybe I'm just giving an example. Then some of these phases, say suppose these phases on the side, they grow very fast at 10 pH. But if I change the pH to maybe 6, then these might not grow fast. This part will grow fast. And that's why simply by monitoring or controlling the pH, you can actually modify the shape. It's very interesting actually. And all these, not only this shape, because the shapes change, there are certain property changes also. Okay. So think about it. It's so easy. The simple process, simply by controlling certain parameters, we can have a huge plethora of nanostructures. Okay. That's how nature has been doing it. Okay. And we are learning from nature. Okay, now let me do one thing. I'll just continue because this is the last slide. Let me just include one more slide, and I will try to explain to you now how these particles start forming. What is the science behind it? What is the physics behind it? What is the chemistry behind it? Okay, so let us start with maybe metallic nanoparticles. Okay, so let me come out of the presentation. Discard the ink annotations. Let me put them in new slide here. Insert.
Excuse me, sir.
Yeah,
Hello. Sir, how you get the parent nanoparticles, sir?
you mean these one?
No, no, sir. There's the sir at the beginning, sir. How you get that nanoparticles, single particles, sir,
Yeah, yeah. See, it's
which
not
you
a
find?
because okay, I understand what you are trying to say. All right. Uh, let me come to that. But see here, all these different shapes that I'm showing you, it's not that it sort of came out from a nanoparticle that formed first and it became these. No, these are actually the formation of the crystal right through. Okay, that means if you look at the first one, when I'm saying nanoparticles, they are actually spherical particles, but they are also going through the process of nucleation followed by ostral ripening. All right. Here, the rod-like structures, the growth process is slightly different because these rods we are sort of fixing on a substrate. It's not suspended particles. Okay, so the process goes on differently. So your answer I'll explain now using another slide. Let me put in a new slide. Let me put in a new slide, blank slide. All right, so uh, let me insert the text box. All right, so let's try synthesis of some metallic nanoparticles. All right, let's try to understand example of some metallic nanoparticles. All right, let's take uh, let's take gold. No, let's take silver. It'll be easier the chemicals. All right, so let's try to make some silver nanoparticles. And oh, I keep forgetting. I have to pick up the pen from below. There it is. Pen. I have to do it for every slide, no? Just a second. I don't know. I can see these below. Where? Ah, yeah, that's it. Pen. I don't know if I selected it. Pen. All right. So, silver. The formula is a chemical formula. The symbol is Az, right? So Az is silver. So let's make some silver nanoparticles now. So, like I said, we need silver atoms in the solution, right? So what do we do? Let's try to make this in water. So we have a beaker where we have maybe water. Okay, so this is water here, H2O. Fine. Ah, H2O. So now uh, we need silver here. So we have to start with some source of silver. That means a silver salt maybe. So let's say we use a very commonly available silver salt, silver nitrate, AZNO3. Okay, that's silver nitrate. Nitrate. Okay, nitrate. And nitrate. All right. It's difficult to write with my stylus, so I don't have to buy another one. Anyway, so we put this one, AZNO3, right? And when we put it in the water, it dissociates. That means, like I said, you will have individual component. So you'll have Az3 plus the moment it is dissolved in water, and 3, 3, NO3, okay, minus. Okay. So basically what is happening here is that, let me remove this part. Where is the, is an eraser here, NO3 minus. All right. So these are the individual ionized. We have silver ions and nitrate ions. Okay. So silver cations, nitrate anions. All right. And what will happen now? Let me use the pen again. So here in the water, we have many of these. Okay, let me just put them as some dot-like structures. All right, we have many of these silver here. All right, all these are silver in the form of Az3 plus. Right, that means this is not a neutral silver atom. Here there are three amounts of positive charges to it, 3 units of positive charges. So where do these 3 units of positive come from? This is because of the absence of 3 electrons, because these are ionic situations. So it's because of the charges, they attract each other and form a molecule. That means Az3 plus is actually, this is forming when from a neutral atom we are removing three free electrons. Okay, we are removing three electrons. Three electrons. All right. So if we remove 3 electrons, then it becomes 3 units of positive charge, because 1 unit of an electron contains 1 unit of negative charge. Right. At the atomic level, we call it 1 unit. So we have all these. So many of them moving here. These are individual atoms with 3 electrons less in the in the atom. Right. Now, what will happen? These are, as I already told you, these are moving around in random motion here. Okay, the typical Brownian motion, they're moving around. And what we want them to come and join together, because we want a silver nanoparticle. Let's suppose say it has 1000 such atoms. That means we have to pull in all these 1000 atoms together to get a nanoparticle like this. All right. So these are constantly in motion. Now, in a stable system, the random motion is such that the atoms do not hit each other. They are all there. So to ensure that they go and hit each other, because they will come together or they will make bonds. So suppose it are here, it will be silver bonds. More silvers coming in, they bond to each other and they will start becoming bigger. And to do that, we need to put some extra energy into the atoms that are moving around. Okay, or I'll say ions, because they are charged. So what we do, we put some energy to it. Let's suppose for this case, we are using thermal energy. Okay, we put in some thermal energy there, and we are getting more excitation in the atoms. Okay, because the thermal energy is going to the atoms, and their movement becomes faster. All right, and they're trying to overcome the barrier that is there, and they want to come together. All right, now look at the situation here. No matter how much we try, so suppose there are two, I'm just saying two, there's one silver ion here and another silver is here. Okay, and I want to bring them together, right? I want to bring them together. So what will happen? Will they come together or will they repel each other? See the condition, they are both positively charged particles now, and there is a natural tendency of repulsion. Positive charges will never attract other positive charges, they will always repel. A positive charge will only attract negative charges, right? So no matter how close we try to take them in, if we try to reduce the distance, that's what we did by putting in more heat here. So if we put the heat here, we are giving more energy here, and we're expecting that they will go and hit and collide with each other. But because of the charges, they repel, they do not allow them to touch each other. Okay? That means if we want all these atoms to come together to form the nanoparticle, we have to first convert these into neutral atoms. That means we have to remove the charges, only then they will come together. because it's not possible that you say, okay, to attract them, let some particles be positive and some particles be negative, which is not possible. All right, because to charge up a particle into negative, you have to pull out the protons or you have to pump in more electrons, right? Which is difficult. But removing electrons is easier, and that's why making positive charge particles is easier. All right, for this case, for these metallic particles, they are always positive. Okay, as long as they're in water. That means in order to convert these into forms like these, which are uncharged, that means if we have two uncharged particles, difficult to work with the stylus. Anyway, see these two Ag together now, they are not charged like the previous ones. Okay, so these are charged, they will never come together or coalesce or become agglomerates, but these can come together if they hit each other. All right, so our first challenge now in the formation of the nuclei for the nanoparticles is that we have to convert these positively charged atoms into neutral atoms. Okay, the charge is 0. Okay, the charge is 0 here. So you say we want to convert Ag3 plus to Ag0. So how do we do that now? Can somebody tell me? How can we do that? Hmm? So if you remember, how did we make the 3 plus? It's because I said we had removed 3 electrons, right? If we remove 3 electrons from a neutral atom, it becomes Ag3 plus in this case. So if we put those 3 electrons back, then it becomes Ag, right? Simply saying, let me remove, sorry, let me grab this part. So it is this same, you know, reaction shown here. So it is Ag minus 3E. That means I need now Ag. So what will I do? I'll move this 3 this side. So it will be, oh sorry, I have to take the pen again. So boring, huh? Let me take the pen again. So all right, and now again. All right, so what is happening now? I will say, oh my god, it's irritating, huh? I can't, I don't know if my eyes are bad or I cannot see the things here. Okay. So what is going to happen now? I'll simply pull in the 3 electrons this side. So it is Ag3 plus 3 electrons. This will give you Az. Do you all agree with me now? We simply plug in to neutralize the 3 positive charges. We simply plug in 3 electrons with 3, 1 unit of negative charge in each. So 3 electrons put in will convert Ag3 plus to Az.
So from where you will get the three electrons, sir?
Exactly. Now that's the question. Where will I get the electrons? Okay. So that is the next phase. So there are certain chemicals which are called, see this process I say here, when you are adding an electron, okay, this process is called reduction. Okay, this is a chemical term called reduction. And if you do this one here, you are removing electrons, okay, then that process is called oxidation, right? The process is called oxidation. Now, all those chemicals that can contribute electrons, that can actually deliver electrons. So the meeting is ending in 5 minutes, so please join back, okay? because there are two classes. Let's continue this discussion. If after this closes, immediately use the same link and come back. Okay. But let me continue till it closes. So all those chemicals that can provide electrons to others are called, because they are helping in the reduction process, they are called reducing agents. Okay. Uh, Reducing agents. So reducing agents have excess of electrons. Okay, and the electrons are not strongly bonded to the nucleus. That means they are constantly in a state of saying, I can give electrons. Okay. Now, if you look at this one, the 3 plus, it is not, it is a case where the atom has less electrons, right? 3 electrons not there. So this atom will constantly try to find out electrons. If it finds, it will automatically take in electrons. Okay, that's a natural tendency because there's something lacking. Now, these reducing agents, they have excess electrons which they can easily donate, right? So what we'll do now to convert this Ag3 into Ag, by giving this these free electrons, we will add into the solution a reducing agent. All right. Now there are many reducing agents. I'll pick up one by one since this is not a chemistry class, and I don't know. I'm not a chemist. Maybe you guys also. I don't know how strong in chemistry we are. We'll try to keep the chemistry as and when necessary. All right. So keeping in mind that we are talking about a reducing agent that can give a lot of electrons. Okay. Now there are many. Say trisodium citrate is a very commonly known reducing agent. Then there's another one called sodium borohydride, okay, which is another a very common reducing agent. So typically for silver synthesis, we always prefer sodium borohydride. So I'll again tell you later as we continue why, but this is suppose this is the chemical NaBH4. All right, sodium borohydride. It has boron, hydrogen, and sodium. Now, sodium borohydride can quickly donate electrons. So the moment we put them, see, we go to an excited state first. That means we put in heat so that we convert everything. That means whatever sodium nitrate, or sorry, silver nitrate we had put in, we need a complete dissociation. That means all the silver nitrates should give out the silver, right? And that's why we sometimes heat it. Like I told you, no, if you put salt in a cold water, it will take a lot of time for mixing. You keep on stirring, right? Heat it up a bit, it instantly dissolves. That means the dissociation is faster. So here heat is using as it's a form of an accelerating agent. The same thing here, and that's why we heat it initially before we add the reducing agent. We heat it up so that all the silver from silver nitrate is released. All right, that means we have all Ag3 plus moving around there. And then we add the sodium borohydride. And then this reaction will happen. So once the reducing agent is given, all the Ag3 pluses will become Ag now. Okay. So now what will happen? Let me find the eraser again. Eraser. Okay. Ah, please bear with me. Okay. We might. Oh, it's not picking up. Why it's not working with the stylus? Some issues. All right. Anyway, till my stylus comes in. So we now have all these uncharged silver in the solution. Okay, in water now. Suppose we are taking water, and we continue with the heating. All right. So the silver atoms